Most people never see the ocean like this. Most people never will. Welcome to Unknown Genesis 4K, where nature shows you the version of itself that textbooks leave out. There is a place on this earth where silence is never truly silent, where even on the calmest of days, beneath the glittering surface and the soft shimmer of afternoon light, something is always moving, always breathing, always waiting. That place is the ocean, and it holds within it a power so vast, so ancient, and so absolute that no human word has ever fully captured it. We have tried. We have called it magnificent. We have called it terrifying. We have called it beautiful. But the ocean does not respond to our descriptions. It simply continues, rising and falling, giving and taking, whispering and roaring, on a timescale that makes human history feel like the blink of an eye. This is not a story about calm waters. This is not a story about golden sunsets reflected in a still and peaceful sea. This is a story about what happens when the ocean awakens in its full fury. When the sky turns the color of bruised iron and the wind begins to climb beyond anything the human body can comfortably stand in. When waves that were gentle swells at dawn become towering mountains of moving water by nightfall. This is the story of the ocean at war with itself, with the sky above it, and with anything and anyone who dares to stand in its path. To understand a storm, we must first understand the ocean's relationship with heat. The sun pours its energy into the sea every single day, warming the upper layers of water across vast tropical expanses. This heat does not disappear. It is stored, absorbed, held in reserve, like potential energy waiting for a trigger. The ocean becomes, in effect, a battery, a colossal thermal reservoir that powers some of the most destructive weather systems the atmosphere is capable of producing. The connection between warm water and violent storms is not a coincidence. It is a direct and measurable relationship, a cause and effect chain that meteorologists have studied for generations and still find humbling in its scale. When sea surface temperatures rise above a certain threshold, roughly 26.5 degrees Celsius, something begins to stir. The warm water heats the air directly above it, causing that air to rise. Moisture travels with it, lifted upward in great invisible columns that feed into the atmosphere. As the air climbs and cools, that moisture condenses, forming clouds and releasing heat in the process. That released heat lowers the atmospheric pressure at the surface, which in turn pulls in more air from the surrounding area. More air means more moisture. More moisture means more lifting, more condensation, more heat release, more pressure drop. The cycle feeds itself, growing in intensity with every rotation, every hour, every mile of warm water it passes over. This is how storms are born. Not with a thunderclap or a sudden dramatic gesture, but with something almost gentle. A slight warmth, a barely perceptible stirring of air, a gradual deepening of cloud cover that might, to a casual observer, seem like nothing more than an overcast afternoon. But the atmosphere is never casual. And what begins as a tropical disturbance, a vague area of unsettled weather drifting westward from the coast of Africa, or forming quietly over the warm waters of the Pacific, has the potential to become something that reshapes coastlines. In the earliest stages, the storm has no identity. It is simply weather, a cluster of thunderstorms rotating loosely around a center of low pressure, disorganized and uncertain. Meteorologists watch it on satellite imagery, tracking its movement, measuring its winds, waiting to see whether it will strengthen or fall apart. Most disturbances never amount to anything. They drift over cooler water, encounter unfavorable wind patterns at higher altitudes, and simply dissolve back into the atmosphere without fanfare. But some of them find exactly what they need: warmth beneath, calm aloft, and they begin to organize. The transformation is not instantaneous, but once it begins, it can be relentless. The scattered thunderstorms start to align, their outflow feeding the circulation, tightening the spiral. The center of the system becomes better defined. Winds near the surface begin to rotate with increasing purpose. The cloud pattern, viewed from above, takes on a shape that any storm chaser or hurricane hunter would recognize immediately: a swirl, a pinwheel, a slow and massive rotation that speaks of enormous and growing power. By the time winds reach sustained speeds of about 63 kilometers per hour, the system is officially classified as a tropical storm. It receives a name. It becomes a named thing, an entity that meteorologists track on their maps and that government agencies issue warnings about. But a tropical storm, for all its power, is still only a beginning. The real escalation comes when sustained winds breach the threshold of 119 kilometers per hour. At that point, what was once a tropical storm becomes a hurricane, or a typhoon, or a cyclone, depending on where in the world it is spinning. Different names for the same phenomenon, different words for the same terrifying force. A mature hurricane is one of the most complex and powerful weather systems that nature produces. It is a machine, but a living one, constantly adapting, constantly feeding, constantly reorganizing itself in response to the environment through which it moves. At its center lies the eye, a column of descending air that creates an area of relative calm and clear skies, sometimes extending 50 or even 60 kilometers in diameter. Inside the eye, the ocean surface may be churned and confused, but the winds are light, the rain has stopped, and the sky above may even show stars. It is a deception of the most profound kind, a pocket of peace wrapped in one of the most dangerous structures in the atmosphere. Surrounding the eye is the eye wall, a ring of the most intense thunderstorms in the entire system. This is where the strongest winds blow, where the rain is heaviest, where the ocean is most violently disturbed. The eye wall is the storm's engine room, the place where the most extreme energy exchange between ocean and atmosphere occurs. Step from the eye into the eye wall, and the world changes instantly. From eerie calm to screaming chaos, from stillness to violence, with almost no transitions between them. It is, by any measure, one of the most abrupt and dangerous boundaries in meteorology. Beyond the eye wall, the storm extends outward in spiral bands of rain and thunderstorms, each one carrying destructive winds and heavy rain, each one capable of producing tornadoes over land. These bands can stretch hundreds of kilometers from the center, meaning that the true footprint of a major hurricane is enormous, far larger than it appears on a standard weather map. A storm centered offshore can be dropping heavy rain on a city 200 kilometers away. Its outer bands can generate rough seas and gusty winds at distances that might seem to someone unfamiliar with tropical systems, impossibly far from the real action. The ocean beneath a hurricane is never passive. The storm stirs the water with tremendous force, creating swells that radiate outward in all directions, carrying the storm's energy thousands of kilometers before finally dissipating on distant shores. The surface of the sea itself becomes almost unrecognizable. Waves from different directions collide and combine, creating confused, chaotic seas where no single wave pattern dominates. Spray is torn from the wave crests by the wind and driven horizontally through the air, reducing visibility to near zero and making the atmosphere feel more like a mixture of water and wind than anything so simple as weather. The waves themselves are among the storm's most dramatic expressions. In a powerful hurricane, wave heights can reach 10, 12, 15 meters or more, walls of moving water that would dwarf a three-story building. These waves do not behave like the gentle swells of a calm day. They are steep, powerful, and irregular, with faces that can break suddenly and violently, releasing enormous amounts of energy in an instant. A ship caught in these seas is not simply rocking and rolling. It is being thrown, lifted, dropped, and struck by forces that can stress even the most robust hull to its limits. For the sailors and mariners who work the ocean for their livelihoods, a storm at sea is not an abstraction. It is the most immediate and tangible reality they will ever face. The experience of a major storm aboard a vessel has been described by those who have survived it as something that is almost impossible to communicate to someone who has never been there. The noise alone is overwhelming. A continuous, layered roar that combines the howl of the wind, the crash of the waves, the groan of the ship's structure, and a kind of low, bass vibration that seems to come from everywhere at once. Visibility drops to nearly nothing. Spray coats every surface. The deck, if it can be accessed at all, is a place where every step is a gamble and every handhold is a lifeline. Inside the hull, the motion is violent and unpredictable. A ship in heavy seas does not simply roll from side to side. It pitches, heaves, yaws, and corkscrews through combinations of motion that make it nearly impossible to stand, to work, or sometimes even to think clearly. Everything that is not secured becomes a projectile. Every surface becomes a hazard. The sounds of the ship working, its frames flexing, its plating responding to the sea's impacts, can be deeply unsettling to those who have not experienced it before, and only slightly less so to those who have. And yet, ships and crews do survive these conditions. They survive because of design, because of training, because of the accumulated wisdom of generations of seafarers who learned, through hard and often brutal experience, how to read the sea and respond to its demands. A skilled navigator in a storm does not simply point the bow at the nearest port and drive forward. They consider the storm's geometry, the direction of the waves, the angle of approach that will minimize the vessel's exposure to the most dangerous seas. They adjust speed constantly, sometimes slowing to a crawl to reduce the impact of wave strikes, sometimes increasing power to maintain steerage in conditions that would otherwise allow the ship to be thrown broadside by a breaking wave. The relationship between a ship and a storm is, in its own terrible way, a dialogue. The sea makes demands. The navigator responds. The sea escalates. The crew adapts. It is a contest without any possibility of victory for the human side. Only survival, only endurance, only the hope of reaching calmer water on the other side. Beyond the immediate physical danger of wind and waves, ocean storms carry with them a suite of secondary threats that can be just as deadly. Among the most feared is storm surge, the phenomenon by which the storm's winds push enormous volumes of seawater ahead of them, piling it up against a coastline until the ocean is running many meters above its normal level. Storm surge is not a wave in the conventional sense. It does not crest and break and recede. It is a sustained rise in sea level, sometimes happening over a period of hours, that can inundate vast areas of low-lying coastal land under meters of salt water. The physics of storm surge are relatively simple, but the consequences are catastrophic. A large, slow-moving hurricane approaching a coastline at an angle can generate surge events that push the sea inland for kilometers, flooding areas that residents had no reason to believe were at any flood risk whatsoever. The water arrives not as a single crashing wave, but as an unstoppable rise, seeping under doors, rising through floorboards, climbing walls with a patience and inevitability that leaves no room for escape for those who have not evacuated in time. The deadliest aspect of storm surge is often its combination with high tide. When a storm arrives at landfall during a period of high tide, the baseline water level is already elevated, and the surge is added on top of it. The result can be water levels that exceed anything previously recorded at that location, inundating areas that even experienced coastal residents believed to be safe. The combination of surge and tide has been responsible for some of the most catastrophic death tolls in the history of tropical cyclones. From the Great Galveston Hurricane of 1900 to the Bangladesh cyclones of the 20th century, to the devastation wrought by storms in the modern era. Once storm surge water has pushed inland, it carries with it everything the sea can gather. Debris from destroyed structures, vehicles swept from roads, boats carried far from their moorings. All of this material becomes part of the moving water, turning the flood into something far more dangerous than water alone. A wall of surge-driven debris can demolish structures that might otherwise withstand the flooding itself. The salt water infiltrates and destroys everything it touches, soaking into walls, corroding metal, saturating soil, killing vegetation. Long after the visible flooding recedes, the damage left behind by saltwater intrusion continues to manifest in the form of mold, structural weakness, soil contamination that can make agricultural land unproductive for years. There is another danger that lurks within storms, one that operates on a different scale and follows different rules than the organized destruction of the hurricane as a system. Rogue waves, sometimes called freak waves or monster waves, are isolated walls of water that can appear with little or no warning in the open ocean, towering to heights that bear no relationship to the surrounding sea state. For centuries, accounts of rogue waves were dismissed by scientists as the exaggerated stories of traumatized sailors, the product of fear and the human tendency to catastrophize extreme experiences. But the instruments do not exaggerate, and as ocean monitoring technology improved, Through the latter decades of the 20th century, the data began to confirm what the sailors had always known. Rogue waves are real, and they are far more common than anyone had previously believed. They form through a convergence of physical factors. Wave energy focusing in certain ocean current patterns, wave trains from different storms interfering constructively, energy concentrating in ways that standard wave models had not fully accounted for. The result is a wave that may be 2, 3, or even 4 times the height of the surrounding sea. A wave that rises from the water like a moving cliff, with a face so steep that it cannot sustain its own weight and breaks with a force that can be measured in thousands of tons per square meter. The Draupner wave, recorded on New Year's Day in 1995 at an oil platform in the North Sea, was one of the first rogue waves to be captured by precise instruments. Its height, just over 25 meters, was recorded against a background of surrounding waves averaging perhaps 10 to 12 meters. It was, by the standards of the pre-instrumental era, the kind of wave that would have been dismissed as impossible. But the platform's sensors recorded it without sentiment or exaggeration, and the scientific community was forced to accept what the data showed. The ocean could generate waves that defied the standard statistical models. The ocean, in other words, could surprise even those who thought they understood it best. For ships at sea, a rogue wave can be an almost instantaneous catastrophe. There is typically no warning. The wave does not announce itself, does not build visibly on the horizon in the way that a distant storm might. It simply rises, faster than the eye can quite track, filling the forward view with a wall of dark water. The impact, when it comes, is unlike anything that can be simulated in training. Windows rated to withstand enormous pressures have been smashed inward. Steel decks have been buckled and torn. Structures that were engineered to survive the worst imaginable sea conditions have been destroyed in seconds. The histories of lost ships, vessels that vanished without distress calls, without wreckage, without any explanation that made sense given what was known about the weather at the time. Now read differently in the light of what we understand about rogue waves. Lightning, too, is a companion to the great storms. In the spiraling rain bands of a tropical cyclone, the atmospheric conditions that generate lightning are present in enormous abundance. Updrafts of tremendous power carry water droplets and ice particles upward through the storm's towering clouds, creating the charge separation that eventually discharges as lightning. Over open water, where there are no tall structures, no trees, no terrain features to serve as preferential discharge points, a ship can become the most electrically attractive object for many kilometers in any direction. A lightning strike at sea is not simply a matter of a bright flash and a loud crack. It carries enormous electrical energy that can travel through a vessel's metallic structure, destroying electronics, overwhelming wiring systems, and, in the worst cases, igniting fires or injuring crew members through secondary current paths. Navigation equipment, communications systems, and propulsion controls can all be disabled in an instant, at exactly the moment when they are most critically needed. A ship rendered navigable by a lightning strike in the middle of a storm is in a profoundly dangerous situation. Suddenly, without the tools it needs to manage its position in seas that show no mercy for those who have lost their ability to respond. The visual spectacle of lightning over the open ocean is one of nature's most dramatic performances. Each flash illuminates the entire seascape for a fraction of a second, freezing the waves in their motion, throwing the storm's cloud structure into sharp relief against the darkness, revealing for a brief instant the full terrible scale of the environment. Then the darkness returns, and the thunder arrives moments later, rolling across the water with a resonance that has no parallel on land. There is something deeply primordial about standing on a deck in a storm, watching lightning walk across the sea, a feeling that has not changed in any essential way since the first human beings looked out from a shoreline at weather that dwarfed their comprehension. The aftermath of a great ocean storm is not simply a scene of damage and debris. It is a complex reorganization of both the natural and human worlds, playing out over timescales that range from hours to years. The immediate aftermath, the torn buildings, flooded streets, downed trees, stranded vessels, is only the most visible layer of the storm's impact. Beneath it, the ocean itself has been changed. Nutrients stirred up from deep water by the storm's mixing create blooms of phytoplankton that turn the sea temporarily green or brown, feeding a cascade of biological activity in the weeks that follow. Sediment disturbed from the seafloor resettles in new patterns. Coral reefs, battered by surge and wave action, may lose decades of growth in a single storm event. On land, the ecological changes wrought by a major storm can persist for generations. Forest ecosystems disturbed by hurricane-force winds undergo succession processes that play out over decades. Coastal wetlands, dunes, and barrier islands are reshaped, sometimes dramatically, by the combined forces of wind, wave, and surge. Species distributions shift. Some habitats are temporarily created while others are destroyed. The storm does not simply subtract from the landscape. It transforms it in ways that are sometimes destructive and sometimes regenerative, often simultaneously. For human communities in the storm's path, the aftermath is defined above all by loss. Loss of property, loss of livelihoods, and sometimes, most devastatingly, loss of life. The economic cost of a major hurricane making landfall in a densely populated area can reach tens of billions of dollars, a figure large enough to affect the finances of entire nations. But economic figures, however large, fail to capture the texture of what storm survivors actually experience. The loss of a home is not merely a financial loss. It is the loss of a place that held memories, identity, and a sense of belonging. The loss of a fishing boat may end not just a livelihood, but a way of life that was passed down through generations. The loss of a community, when enough families choose not to rebuild, when enough businesses fail to reopen, can be permanent, leaving behind empty lots and overgrown foundations where a living neighborhood once stood. Recovery is always slower and harder than the optimistic projections made in the storm's immediate aftermath suggest. Insurance disputes, bureaucratic delays, material shortages, and the sheer physical labor of clearing debris and rebuilding structures all conspire to extend the period of disruption far beyond what the calendar of a typical political news cycle can sustain. Communities are still recovering from storms that struck a decade ago, while new storms are already forming over warm water, already gathering the strength that will be unleashed on the next shoreline in their path. The climate context of all of this is inescapable. The ocean is warming. Not uniformly, not everywhere at the same rate, but the overall trend is unmistakable in the data and increasingly visible in the behavior of the storms themselves. Warmer sea surface temperatures mean more energy available for tropical cyclone intensification. A storm that might, under the conditions of 50 years ago, have reached Category 2 intensity may now have the thermal energy available to reach Category 4 or 5. The difference in destructive potential between those two levels is not merely quantitative, it is qualitative. A Category 5 hurricane does not simply do more damage than a Category 2. It does a fundamentally different kind of damage to a fundamentally wider area with a fundamentally reduced ability for human infrastructure to withstand it. Rapid intensification, a phenomenon in which a storm's maximum sustained winds increase by at least 50 kilometers per hour within a 24-hour period, has become more common as ocean temperatures have risen. This is perhaps the most operationally dangerous consequence of warming seas for coastal communities, because it compresses the warning timeline. A storm that is a tropical storm on Tuesday morning and a major hurricane by Tuesday evening gives emergency managers and coastal residents far less time to prepare and evacuate than a storm that follows a more gradual intensification path. The logistical infrastructure of evacuation, the buses, the fuel, the shelter capacity, the traffic flow on evacuation routes requires time that rapid intensification does not always provide. Rising sea levels compound the storm surge problem in a way that is mathematically simple but practically profound. When the baseline sea level rises, the same surge event that previously flooded only the lowest lying areas now reaches farther inland. A surge height that was considered a worst-case scenario in 1980 may become a relatively routine outcome for a moderate storm by 2050. The geography of coastal flood risk is being redrawn, quietly and continuously, by the millimeters of sea level rise that accumulate year by year. Coastal communities are, in many cases, still making infrastructure decisions based on flood maps that reflect the risk of a world that no longer exists. The societies most vulnerable to intensifying ocean storms are often those least responsible for the conditions that are making them worse. Small island nations in the Pacific and Caribbean, with minimal industrial histories and minimal carbon footprints, face existential threats from storms supercharged by a warming that they did nothing to cause. Low-lying river delta communities in South Asia, where hundreds of millions of people live in some of the world's most agriculturally productive but geographically precarious landscapes, face recurring inundation from storms whose intensity is being amplified by global processes far beyond their influence or control. The geography of climate vulnerability and the geography of climate responsibility are, to a disturbing degree, mirror images of each other. And yet, the human response to ocean storms is not only a story of vulnerability and loss, it is also a story of extraordinary adaptation, resilience, and the deep human will to understand and survive the forces of the natural world. The science of hurricane forecasting has advanced enormously over the past half-century. Satellites monitor storm systems around the clock from orbit. Aircraft penetrate the eye walls of hurricanes to take measurements from within the most dangerous environments on Earth. Computer models run on machines of staggering computational power to project storm tracks and intensities with an accuracy that would have seemed miraculous to a forecaster working in the 1970s. The average error in a 48-hour hurricane track forecast is now smaller than the radius of a large city. Emergency management systems have improved correspondingly. Evacuation orders are issued with greater lead time. Shelter networks have expanded. Communication systems have become more reliable and more redundant. Public awareness of storm surge risk, historically one of the most underestimated storm hazards, has improved significantly, though it still has far to go. Building codes in hurricane-prone regions have been strengthened, incorporating lessons learned from each successive storm about how structures fail and how they can be made more resistant. The ocean, of course, knows nothing of any of this. It does not register the satellites overhead or the forecast models running in climate centers on every continent. It simply continues its ancient business of absorbing heat, transferring energy to the atmosphere, generating the storms that have always been part of its relationship with the air above it. The storms have always been there, long before there were any humans to give them names or build houses in their paths. They will continue long after whatever mark human civilization leaves on the planet has been weathered away by the very forces they represent. What has changed is the scale of human exposure and the conditions under which these storms form and strengthen. Coastal populations have grown enormously. Infrastructure of immense value has been built on low-lying land within striking distance of storm surge, and the thermal energy available to feed and intensify tropical cyclones has increased as the ocean has warmed. The storms are, in a very real sense, operating with a larger energy budget than they did a century ago. The consequences of that larger budget are already visible in the data. In the increasing proportion of the strongest storms, in the more frequent rapid intensification events, in the storm's surge impacts that now reach areas previously considered safe. To watch footage of a great ocean storm from the safety of distance, from a screen, from a high structure on land, from a position of warmth and shelter, is to experience something that oscillates constantly between awe and dread. The sheer visual scale of a major hurricane from satellite imagery, the perfect spiral of cloud spanning hundreds of kilometers of ocean, has an aesthetic power that is independent of its destructive potential. It is, objectively, one of the most organized and impressive structures that the atmosphere produces. The science that underlies it is elegant in its internal logic, even as its consequences are devastating. Up close, the aesthetic gives way entirely to the physical. The sound of hurricane-force winds is not like the sound of any other weather event. It occupies frequencies that the body feels as much as the ears hear. It vibrates structures. It overwhelms conversation. It makes thought difficult, combined with the visual chaos of flying debris, horizontal rain, and a sky that has lost all its familiar blue to become a gray-green darkness. The sensory experience of being within a major storm is one that survivors consistently describe as unlike anything else they have ever encountered. The sea in the heart of a storm is no longer recognizably the sea. The distinction between air and water becomes blurred as spray fills the atmosphere and waves break continuously into foam. Individual waves lose their identity in the general chaos of the surface. The horizon, that fundamental reference point of maritime navigation, disappears entirely behind walls of spray and rain. The world contracts to the immediate, the next wave, the next gust, the next second of maintaining position and balance and control. All of the broader context of the storm, its size, its track, its intensity on the meteorological scale, becomes irrelevant to the individual trying to survive within it. And then, eventually the storm passes. The winds ease. The waves, though still high, begin to lose their steepest and most aggressive faces. The rain thins from a roaring downpour to something that merely qualifies as heavy. The sky begins gradually to lighten. The long swells that will carry the storm's energy across thousands of kilometers of open ocean before finally dissipating on some distant beach are already moving outward, the last physical signature of the storm's passage, outlasting the storm itself by days. In the quiet that follows, there is a particular quality of light and air that storm survivors often remark upon. The atmosphere has been washed clean. Colors seem more vivid. The ocean, still running in long confused swells, glitters differently than it does on an ordinary day. There is something in the post-storm world that feels almost clarified, stripped down to essentials by the passage of something enormous and indifferent and entirely natural. The ocean does not mourn the damage it has caused. It does not celebrate the passage of the storm. It simply continues its processes, its currents, its tides, its slow absorption of atmospheric gases, its vast biological cycles that support half the oxygen production on the planet. The storm was part of all of this, a mechanism for moving heat from the tropics toward the poles, for mixing the ocean's layers, for transferring energy between sea and sky. It was violent, and it was destructive, and it was, from the ocean's perspective, entirely unremarkable. Storms like this have been happening for as long as there has been a warm ocean and a rotating planet to set them spinning. That continuity, the sense that these storms are older than any human culture, any human language, any human concept of disaster or recovery, is perhaps the most humbling aspect of everything that ocean storms represent. We measure them with instruments. We name them to track them. We build walls and evacuation plans and building codes to mitigate their impact. We study them, model them, and attempt to forecast them with increasing precision. But we do not control them. We do not negotiate with them. We endure them, as our ancestors endured them, and as our descendants will endure them, hopefully armed with better tools, better data, and better collective will to protect the communities that stand in their inevitable path. The story of ocean storms is ultimately a story about the relationship between a species that builds and a planet that does not hold still. It is a story about the extraordinary power of the natural world, about the limits of human ingenuity in the face of atmospheric physics, and about the resilience that emerges, again and again, from the communities that are rebuilt in the wake of each successive disaster. Every storm leaves scars. Every storm also leaves lessons, if we are willing to learn them. The ocean will continue to warm. The storms will continue to form. The waves will continue to rise, driven by winds that owe nothing to our plans or our hopes or our fears. And the sea, vast, indifferent, ancient, and magnificent, beyond any adequate description, will remain what it has always been. The most powerful force on the surface of this planet, and the great humbling constant against which all human ambition is ultimately measured. This is the ocean in its fury. This is the storm in its full and terrible expression. And this raw, unrelenting, magnificent violence is the oldest story the Earth knows how to tell. There are places in the world where the storms arrive not as occasional catastrophes, but as seasonal rhythms, as predictable in their timing as the harvest or the monsoon rains. The Western Pacific Basin is one such place. Known as the most active tropical cyclone basin on Earth, it generates more named storms per year than any other region, and it does so with a consistency that speaks to the extraordinary thermal resources of that part of the ocean. The warm pool of water in the Western Pacific, where sea surface temperatures can reach 30 degrees Celsius or higher across enormous expanses, is a furnace that feeds storm after storm throughout the typhoon season. The statistics of this basin alone are staggering. In some years, the Western Pacific generates 30 or more named storms, including multiple super typhoons. Storms whose sustained wind speeds exceed 250 kilometers per hour, and whose destructive potential puts them in a category that the standard Saffir-Simpson scale was not originally designed to capture. Communities living within reach of these typhoons have developed over generations a cultural relationship with storms that is unlike anything found in regions where hurricanes are rarer and less predictable. The architecture reflects it. The agricultural cycles reflect it. The language reflects it. Older inhabitants of the Philippine Islands or the coastal communities of southern Japan carry within them a knowledge of storms that is not found in any meteorological textbook. It is a familiarity born from experience, from watching the sky change, from feeling the way the wind shifts before a system approaches, from understanding what the behavior of birds and the color of the sunset and the quality of the morning air can tell you about what the next 48 hours will bring. This traditional knowledge is not superstition. It is the distillation of centuries of observation by people whose survival depended on reading the natural world with extraordinary precision. The formal science of meteorology has in many cases confirmed what these communities already knew. Certain cloud formations, certain wind shifts, certain patterns of swell arriving from a particular direction are reliable precursors to severe weather. The integration of traditional ecological knowledge with modern forecasting systems is a conversation that is still very much in progress, and the potential of that integration to improve community-level preparedness in storm-prone regions is significant and increasingly recognized by the scientific community. The Bay of Bengal, flanked by the Indian subcontinent to the west and north, and by the arc of Southeast Asia to the east, is another of the world's most historically devastating cyclone basins. Its geography creates conditions that amplify the destructive potential of the storms that form there. The bay is essentially a funnel, wide at the south and narrowing as it extends northward toward the low-lying coasts of Bangladesh, West Bengal, and the Irrawaddy Delta of Myanmar. When a cyclone moves northward into this funnel, the storm surge it generates has nowhere to spread laterally. Instead, it piles up against the land, reaching heights that can be catastrophic for the tens of millions of people who live on deltas and coastal plains barely elevated above sea level. The shallow seafloor of the northern bay amplifies the surge further, compressing the water column into heights that would not be generated by the same storm over deeper water. The history of Bay of Bengal cyclones is written in extraordinary loss of life. The Bola cyclone of 1970 killed an estimated 300,000 people in what was then East Pakistan, a death toll so staggering that it remains one of the deadliest natural disasters in recorded history. Subsequent decades brought further catastrophic storms to these same coasts, each one teaching painful lessons about the intersection of extreme weather and concentrated coastal poverty. The improvements in forecasting, in cyclone shelter construction, and in evacuation logistics that followed these tragedies have saved hundreds of thousands of lives in subsequent storm events. Bangladesh's cyclone preparedness program is now held up as a model of what early warning systems and community-level preparation can achieve even with limited resources. But the underlying geographic and social vulnerability remains, and each storm season brings renewed anxiety to communities that know better than anyone what these storms can do. The Arabian Sea, historically a less active cyclone basin than either the Bay of Bengal or the Western Pacific, has in recent decades produced storms of unexpected intensity. Warming sea surface temperatures have increased the energy available to systems forming there, and storms that would previously have weakened before reaching land have instead intensified, striking the coasts of Oman, Yemen, Pakistan, and India with a ferocity that surprised both the scientific community and the affected populations. The increasing activity of this basin is one of the more dramatic recent examples of how warming oceans are changing the geographic distribution of tropical cyclone risk, potentially bringing severe storms to coastlines that have not historically needed to prepare for them, and whose populations and infrastructure may be entirely unprepared for what such a storm can do. The South Indian Ocean and the waters around Australia present yet another set of storm dynamics. Tropical cyclones in these regions, called cyclones, like their Bay of Bengal cousins rather than hurricanes or typhoons, form in waters that are warming at rates comparable to or exceeding the global average. The northwestern coast of Australia has experienced some of the most intense tropical cyclones ever recorded anywhere in the world, with systems developing over the exceptionally warm waters of the Timor Sea and sweeping ashore across sparsely populated coastlines where the infrastructure, though more robust than in many developing world storm zones, is tested to its limits by the frequency and intensity of landfalling events. The Atlantic Basin, though not the most active in terms of storm frequency, has historically been the most studied and the most expensive in terms of economic damage. largely because of the concentration of wealthy, densely populated coastlines on both sides of the basin and throughout the Caribbean. The Gulf of Mexico and the Caribbean Sea present particular hazards because of the shallow, warm water that makes rapid intensification not just possible but likely when storms move over them. A storm that is a modest tropical system entering the Caribbean may be a dangerous major hurricane by the time it reaches a populated island, having fed on the extraordinary thermal energy concentrated in those warm, enclosed seas. The Caribbean islands present a particular case study in the intersection of geography, economic vulnerability, infrastructure limitations, and storm exposure. Many of the smaller island nations in the region have minimal land area at higher elevations, meaning that storm surge from a major hurricane can inundate a significant fraction of the island's total habitable territory. Their economies are often heavily dependent on tourism and agriculture, both of which are devastated by severe storms and take years to fully recover. Their infrastructure, built with limited resources, may not meet the engineering standards that offer meaningful protection against the strongest hurricane winds. And their geographic isolation means that post-storm relief and reconstruction supply chains must operate across open water, adding cost and delay to an already enormous logistical challenge. The 2017 Atlantic hurricane season demonstrated what a sequence of major storms can do to a region's accumulated infrastructure, economy, and social fabric. Systems arriving one after another, with insufficient time between them for affected communities to assess damage and begin recovery before the next storm arrived, left entire islands stripped of virtually every tree. Power grids that had taken decades to build were destroyed in hours. Communities that had rebuilt from previous storms found themselves starting over again, confronting the exhausting and demoralizing question of whether the cycle of destruction and reconstruction made any long-term sense at all. The answer to that question, in all its difficulty and all its human complexity, lies at the heart of one of the most challenging policy debates of the coming decades. How do coastal communities adapt to a world of intensifying storms? Do they rebuild in place, investing in stronger infrastructure, higher seawalls, and more robust building codes? Do they engage in managed retreat, the deliberate and planned relocation of vulnerable communities to higher ground, accepting the loss of ancestral lands and established community structures in exchange for greater long-term safety? Do they pursue some combination of the two, protecting the most economically and culturally critical areas while allowing others to be reclaimed by the sea? There are no easy answers, and the communities most directly affected by these questions often have the least political and economic power to influence the decisions being made on their behalf. The politics of climate adaptation are complicated by issues of justice, of historical responsibility for the emissions that are driving the warming, and of the enormous short-term costs of building for long-term resilience. The science can tell us with increasing precision what the future of storm risk looks like under various emission scenarios. It cannot tell us how to navigate the human dimensions of responding to that future, the cultural attachments to place, the political economies of coastal development, the distributional questions of who pays for adaptation and who benefits from it. One of the most important frontiers in current storm science is the attempt to predict rapid intensification with greater accuracy. The physical conditions that enable a storm to jump from a moderate tropical system to a major hurricane in a matter of hours are now reasonably well understood in broad terms. Warm, deep water beneath the storm's track, low wind shear in the atmosphere above the storm that would otherwise disrupt its organized circulation, a well-defined and strengthening inner core structure. But the precise prediction of when and how quickly a specific storm will intensify has remained one of the hardest problems in operational meteorology. The difference between a system that stabilizes at modest intensity and one that explosively strengthens in the hours before landfall can be the difference between an event that emergency management systems can handle effectively and one that overwhelms every preparation. Aircraft reconnaissance has been central to hurricane science for generations. The hurricane hunters fly directly into the cores of tropical cyclones, sometimes making multiple passes through the eye wall at altitudes where conditions are severe enough to test both the aircraft and the crews who fly them. The data they collect, wind speeds, temperatures, pressures, humidity profiles at multiple levels through the storm's vertical structure, feeds directly into the forecast models and provides ground truth that satellite observations alone cannot supply. Without these data, the accuracy of intensity forecasts would be significantly reduced, and the uncertainty in track predictions over shorter time ranges would be correspondingly higher. The human willingness to fly into the most dangerous atmospheric structures on Earth in the service of the data that protects millions of people on the ground is one of the less celebrated but genuinely remarkable features of modern storm science. The development of unmanned systems for hurricane reconnaissance is an active area of research that holds considerable promise. Drones capable of sustained flight through hurricane conditions, including the extreme turbulence and updrafts of the eye wall, could potentially provide continuous, real-time data from the storm's core without putting human crews at risk. The data gaps that currently exist in understanding of inner core dynamics, where the most critical intensity changes occur, and where the interactions between the storm's circulation and the ocean's surface are most intense, might be partially filled by systems that can maintain station in areas where manned aircraft must operate with more caution. Ocean-based observations are equally critical to storm science and forecasting. Networks of surface buoys distributed across the ocean basins continuously measure sea surface temperature, wave height, wind speed, and atmospheric conditions at the sea surface. Profiling instruments drifting at various depths track the temperature structure of the water column in ways that help forecasters understand the depth of warm water available to fuel storm intensification. When a storm moves over a shallow warm layer, its own winds can mix cooler water up from below, effectively cutting off its heat supply and leading to weakening. When the warm water extends deep, the storm can continue to intensify with little constraint from this feedback. Understanding this subsurface ocean structure in near real time is essential to making accurate intensity forecasts. All of this data flows into numerical weather prediction models of extraordinary sophistication. These models solve systems of equations, representing the physics of fluid dynamics, thermodynamics, and moisture processes across millions of grid points in 3 dimensions, updated continuously as new observations arrive from satellites, aircraft, buoys, and surface stations. The ensemble systems that modern forecasting agencies run attempt to capture the inherent uncertainty in the atmosphere's future evolution by producing multiple forecast simulations that differ slightly in their initial conditions or model physics, yielding a range of possible outcomes that conveys not just the most likely scenario, but the spread of possibilities around it. This probabilistic approach to forecasting, communicating uncertainty honestly, rather than presenting a single deterministic prediction, is one of the most important advances in operational meteorology of the past 2 decades. Track forecasts have improved dramatically. A 5-day hurricane track forecast today is approximately as accurate as a 3-day forecast was 20 years ago. The skill has accumulated through investment in better models, better observations, better data assimilation techniques, and better understanding of the large-scale atmospheric patterns that steer tropical cyclones. But intensity forecasting, predicting not just where a storm will go, but how strong it will be when it gets there, has improved more slowly and remains an area where the gap between scientific aspiration and operational capability is still substantial. The physical processes that govern intensity change operate on scales that are difficult to observe and difficult to simulate numerically, and the coupling between the ocean and the atmosphere in the immediate vicinity of the storm's core involves interactions of great complexity. Beyond the physical sciences, the social dimensions of storm response and recovery have become increasingly important areas of study. Understanding why people make the decisions they do in the face of storm warnings is not simply a matter of academic interest. It has direct implications for how emergency management systems communicate risk, issue warnings, and structure evacuation orders. Research has consistently shown that the simple transmission of accurate technical information is insufficient to produce the protective behaviors that emergency managers seek to encourage. People make evacuation decisions in social contexts, weighing not just the communicated probability of harm, but their own experience of previous storms, their assessment of the source of the warning, their concern for property and pets they cannot take with them, their obligations to family members who cannot evacuate without assistance, and their judgment of the social consequences of leaving when their neighbors are staying. The answer that emerges from this research is that vulnerability to storm impacts is not primarily a function of geography alone. It is a function of social conditions that determine both how exposed people are to the physical hazard and how much capacity they have to respond to it. The same storm, striking 2 communities with similar geographic exposure, can produce dramatically different outcomes depending on which community has stronger social networks, greater economic resources, more trusted local leadership, better access to early warning information, and greater capacity for collective action. The physical hazard is the same. The social context that determines how people experience and respond to it is what differentiates a manageable emergency from a long-term catastrophe. This understanding has shifted the emphasis in disaster risk reduction toward approaches that address the social determinants of vulnerability alongside the purely physical dimensions of storm protection. Stronger buildings and better seawalls are important and necessary. But so are community organizing, economic development, political representation for historically marginalized coastal populations, access to education and health services, and the social trust that allows communities to respond collectively to threats rather than fragmenting under pressure. The most storm-resilient communities are not necessarily those with the most advanced physical infrastructure. They are often those with the strongest social fabric, the deepest reserves of mutual aid, and the most extensive experience of having survived previous storms together. The insurance industry, which has more direct financial exposure to storm risk than almost any other economic sector, has been grappling with the implications of intensifying storms for decades. Storm losses have increased dramatically in absolute terms, driven partly by more intense storms and partly by the enormous increase in the value of property and infrastructure located in storm-vulnerable coastal zones. The industry's models, built on historical loss data, struggle to keep pace with a changing risk environment where the past may no longer be a reliable guide to the future. Premiums have risen sharply in the most exposed markets. Coverage has been withdrawn entirely from some of the most vulnerable areas. The private market's progressive retreat from certain coastal risk pools is forcing governments to step in as insurers of last resort, socializing costs that the private sector has determined it can no longer absorb at rates that policyholders are willing or able to pay. The implications of this shift extend far beyond the insurance market itself. Property values in the most exposed coastal areas are beginning to reflect, with a lag, the growing recognition that storm risk is increasing, and that the social infrastructure of insurance, emergency management, and government reconstruction assistance that has historically allowed coastal communities to rebuild may not be as reliable in the future as it has been in the past. The concept of managed retreat is moving from the academic literature into actual policy discussions in a growing number of jurisdictions, driven not by a top-down imposition of environmental values, but by the hard arithmetic of repeated losses, rising insurance costs, and the growing difficulty of securing financing for property in areas where lenders have begun to price climate risk into their underwriting decisions. The ocean does not participate in any of these human deliberations. It continues its ancient circulation patterns, the great overturning currents that carry warm water from the tropics toward the poles and dense, cold water from the polar depths into the abyss. These circulation systems are themselves being modified by a changing climate, altered by the input of fresh water from melting ice sheets, by the changing temperature gradients between the equatorial and polar regions, by feedbacks between ocean heat content and atmospheric circulation that are still being understood. The changes in storm behavior that we are already observing are, in a sense, only the most visible and dramatic symptom of a much larger reorganization of the global climate system that is still in its early stages and whose full consequences will unfold over timescales that extend well beyond any current political or economic planning horizon. The deep ocean, largely invisible and poorly monitored, plays a role in long-term climate regulation that is still being fully characterized. It absorbs heat from the atmosphere at an extraordinary rate, buffering the warming that would otherwise be even more rapid. It takes up carbon dioxide from the air, processing it through chemical reactions that alter the ocean's acidity and affect marine ecosystems in ways that are already detectable and are expected to intensify. It stores energy that will eventually be released back into the atmosphere, sustaining and amplifying the storms of decades and centuries to come. To understand what the storms of the future will look like, we must understand the ocean not just at its surface but in its depths, a realm that remains in many ways less well mapped and less well monitored than the surface of other planets. There is something philosophically significant about the contrast between the precision of modern storm forecasting and the deep uncertainties that attend projections of storm behavior over longer timescales. Under a changing climate, we can forecast with considerable accuracy where a specific tropical cyclone will be in 3 or 4 days. We can estimate with reasonable confidence the range of intensity it is likely to achieve. We can model the storm surge it will produce for various landfall scenarios and translate those outputs into practical guidance for emergency managers. This is a genuine achievement of applied science, accumulated through decades of research investment, international cooperation, and the patient accumulation of observational data. And yet, the trajectory of storm hazard over the coming half-century remains characterized by uncertainties that no amount of additional computing power will entirely resolve. The feedbacks between warming oceans, changing atmospheric circulation patterns, and tropical cyclone behavior are complex enough that the range of possible futures remains wide. The direction of travel is clear enough. More energy available to intensify storms, higher baseline sea levels amplifying surge impacts, more atmospheric moisture available to produce catastrophic rainfall even from weakening systems over land. But the specific timing and magnitude of these changes and the ways in which they will interact with regional climate variability remain active areas of research. Living with this uncertainty, making decisions about coastal development, infrastructure investment, emergency management policy, and land use in a risk environment that is known to be changing but cannot be precisely characterized, is one of the defining governance challenges of the 21st century. The tools of decision analysis under uncertainty offer frameworks for making rational choices when the future is not fully knowable. But those frameworks must be applied within political and institutional systems that have their own incentive structures, their own planning horizons, and their own internal pressures that do not always align with the demands of long-term risk management. The result, too often, is that the decisions that would most effectively reduce future storm impacts are deferred in favor of responses to the immediate and the visible. The great navigators of history understood something about this that the modern world sometimes forgets. The Polynesian wayfinders who crossed the vast Pacific in outrigger canoes, using only the stars, the ocean swells, the behavior of birds, and the feel of the wind against their skin as their instruments, were not navigating in the absence of uncertainty. They were navigating in conditions of profound uncertainty, with consequences for error that were absolute and immediate. Their skill lay not in eliminating uncertainty, but in managing it in gathering every available signal from the environment, in drawing on accumulated community knowledge that represented generations of experience with the ocean's patterns, and in making decisions that maximized the probability of survival while remaining flexible enough to respond to conditions that departed from expectation. The sailors and maritime communities that have lived in close relationship with the ocean throughout history developed not just navigational knowledge, but a philosophical orientation toward the sea that is in some ways more sophisticated than the relationship that modern coastal societies have with it. They did not assume that the ocean was controllable or that the right infrastructure could protect them from its worst moods. They worked with the ocean's patterns rather than against them, building their lives and their communities around a realistic assessment of what the sea would and would not tolerate. They knew when to venture out and when to stay ashore. They knew what signs to read and what the consequences of misreading them would be. And they built into their cultures the stories, the practices, and the knowledge systems that allowed this wisdom to be transmitted from one generation to the next. The modern world has in many respects lost this orientation. The combination of powerful engineering, and confident optimism that characterized much of the 20th century's approach to coastal development proceeded on the implicit assumption that human technology could master the natural hazards of the coast, or at least manage them to a degree that made any level of coastal development rational and safe. Seawalls were built and deemed protective. Levees were raised and declared adequate. Building codes were written and, in many jurisdictions, inadequately enforced. Flood maps were drawn on the basis of historical data that did not account for future changes in the hazard environment, and then used to make decisions about insurance requirements and land use that would shape coastal development for decades. The storms have been correcting these assumptions one by one at enormous cost. Each major event adds to the empirical record of what happens when the hazard exceeds the engineering. Each wave of destruction that overtops a seawall, each flood that inundates a zone designated as low risk, each building that fails at wind speeds it was supposedly designed to withstand, is a data point in an argument that the ocean is making continuously and that human institutions are only slowly learning to hear. The argument is not complicated. It is simply this: the ocean is not a fixed and predictable hazard that can be permanently managed by sufficiently clever engineering. It is a dynamic and changing force whose capabilities are themselves changing in response to conditions that human activity has helped create. Hearing and responding to this argument requires a kind of institutional humility that does not come naturally to systems built around the assumption of technical mastery. It requires being willing to say that previous assessments of risk were wrong, that structures and communities we invested in protecting may need to be reconsidered, that the cost of continuing to subsidize coastal development in the highest risk zones may eventually exceed the cost of supporting those communities in relocating to safer ground. These are difficult things to say and harder things to act upon, because they conflict with established interests, with cultural attachments to place, and with the political calculus of systems in which the concentrated costs of decisions fall on identifiable constituents while the diffuse benefits of risk reduction are harder to see and harder to claim credit for. And yet, the direction of travel is becoming clearer. Driven partly by the escalating costs of storm damage, partly by the growing difficulty of insuring and financing high-risk coastal property, and partly by the slowly increasing recognition in affected communities themselves that the old normal may not return, the conversation about managed retreat and climate adaptation is gaining ground in a way that it had not a decade ago. The question is no longer whether these conversations need to happen, but how to have them in ways that are just, that protect the most vulnerable, that preserve what is culturally and economically valuable, and that are realistic about what can be accomplished within the time available before the next major storm arrives. Because the next major storm will arrive. It is not a question of possibility, but of probability, and the probability is not low. The ocean basins that generate tropical cyclones are active every season. The conditions that favor storm intensification, warm water, low wind shear, a humid and unstable atmosphere, are present somewhere on Earth for much of the year. And the coastal zones that are most exposed to storm impacts are, in most cases, also among the most densely populated and economically active regions on the planet. The exposure is not going away. The hazard is intensifying. The question of how to manage the intersection of those two realities is one that will define the relationship between human civilization and the ocean for the rest of this century. The sea does not wait for us to resolve these questions. It continues its ancient business of absorbing heat, generating storms, moving energy around the planet, shaping coastlines, and reminding any creature foolish or unfortunate enough to be caught in its worst moods that the scale of nature's power makes the scale of human ambition look very small indeed. Every wave that crashes on a shore is carrying energy from somewhere, from a storm hundreds or thousands of kilometers away, from the accumulated heat of a summer's worth of sunlight, from the deep currents that circulate through the ocean's abyssal plains on timescales measured in centuries. The ocean is always in motion, always transporting energy and matter, always responding to the forces that act upon it. To stand at the edge of the sea before a storm and to watch the swells arriving, each one carrying the distant signature of the system that generated it, is to feel the connection between the local and the global in the most direct and physical way. The wave that lifts the sand at your feet was generated by wind that blew thousands of kilometers away, over water that was warmed by sunlight that began its journey 93 million miles from here. The storm that is coming has been growing for days over a patch of ocean that you will never see, drawing its energy from a warming that reflects the accumulated output of a century of industrial civilization. Everything is connected to everything else, and the connection is not abstract. It arrives at the shoreline as a physical force, felt in the chest and heard in the roar. This is the ocean. This is the storm. This is the oldest and most powerful story the natural world tells, told again and again, in every ocean basin, in every storm season, to every generation that has ever lived close enough to the sea to feel its breath. The story does not have a resolution, only a continuation. The waves keep coming, the storms keep forming. The ocean keeps warming and rising and changing in ways that will shape the lives of people not yet born, on coastlines not yet built, in communities not yet imagined. We are the generation that knows what is coming and still has the capacity to change how bad it gets. That is not a comfortable position, but it is an important one. The ocean has been patient with us in its way. It has absorbed our carbon and our heat and our indifference to its limits. It has continued to provide the rainfall, the fisheries, the climate regulation, and the beauty that have sustained human civilization since before recorded history. It asks nothing from us in return, because it does not ask anything from anyone, but it reflects, with perfect physical fidelity, what we have put into it. And what we have put into it is now coming back to us in the form of storms that are stronger, surges that rise higher, floods that reach farther inland, and a level of coastal risk that is still rising with every passing year. The stories we tell about ocean storms matter. They matter because the way we talk about these events shapes the way we understand them, and the way we understand them shapes the decisions we make in response. When we describe storms only in terms of their immediate drama and destruction, we miss the deeper story of why they are becoming more dangerous and what we might do about it. When we tell only the story of loss, we miss the story of resilience and adaptation that communities always find ways to write in the aftermath. And when we forget to tell the story of the ocean itself, its depth, its history, its central role in the functioning of the planet, we lose the perspective that might help us treat it with the respect that its power demands. Every ocean storm is a lesson, if we are willing to receive it. Every wave is a message from the system that sustains us. And the ocean, endlessly patient and endlessly powerful, will keep sending those messages whether we read them or not. The question has always been, and remains, whether we are paying enough attention to understand what they say before it is too late to act on the knowledge. The storm begins far away over warm water. It always has. It always will. And somewhere on this planet, even as these words reach your ears, another disturbance is forming over a sun-warmed sea, gathering itself slowly into something that will, in days or weeks, become a force that reshapes coastlines, tests communities, and reminds us once again of the power that lies at the heart of the world's greatest ocean. We have always lived in the shadow of the storm. We always will. The only question is how wisely we choose to live there.